Just a moment.
This is the chairman, right?
Yes. Hello. Hello. Good morning,
Hello.
everyone. My name is Dushyant Chauhan, and I would like to introduce our session chair, Dr. Shad Akhtar, who is Assistant Professor at IIT Delhi. Now, Dr. Shad Akhtar will welcome our keynote speaker, Dr. Soujanya Poria, and from here, Dr. Shad Akhtar will take control of this session.
Thank you, Dushyant. Okay. So, on behalf of ICON 2020, a warm good morning to all of you and welcome to the day 2 of the conference. Today, we have Dr. Soujanya Poria with us to give an invited talk on the topic toward investigating and interpreting the role of context in utterance-level dialogue understanding. Dr. Soujanya Poria is an assistant professor of computer science at the Singapore Institute of Technology and Design, Singapore. He holds a PhD degree in computer science from the University of Stirling, UK. Soujanya was a recipient of the prestigious early career award called NTU Presidential Postdoctoral Fellowship in 2018, which offers him a research grant worth $150,000 US. Before taking up the presidential fellowship position at the NTU, he was a scientist at the A-Star and Temasek Laboratory, NTU. He is also a PI of multiple academic and industrial grants with the amount totaling 1.5 million US. He has co-authored more than 100 papers published in top-tier conferences and journals such as ACL, EMNLP, AAAI, NACL, Neurocomputing, Computational Intelligence Magazine, etc. At present, he is also affiliated with A-Star Singapore as a senior scientist. He was an area co-chair at several ACL, NACL, EMNLP conferences and a publicity chair at StarSem 2019. He served as a senior PC member at IIIT 2019, HKI 2019, and often serves as a PC member in reputed conferences such as ACL, EMNLP, HKI, NACL. He has given several invited talks at venues like Sickling 2018, Social NLP 2019, and MICAI 2020. He has Google Scholar citation of more than 9,000 and his H index is 45. Recently, he has been awarded the IEEE CIM Outstanding Paper Award. 3 of his papers are listed as Web of Science highly cited papers in the field of computer science. Recently, in an article published in the Journal of Information Science, he has been listed as one of the most profitable and impactful researchers from 2000 to 2016 in the field of sentiment analysis. Soujanya is Associate Editor of Cognitive Computation, Information Fusion, and Neurocomputing. So, without any further ado, I welcome Dr. Soujanya Poria. We are lucky to have you. So, over to you. Thank you.
Thank you so much, Shad. It's my pleasure. So, yeah, let me quickly share my screen. Okay, I hope my screen is visible.
Yes.
Okay, great. So a little bit of introduction about the topic. This topic is about dialogue understanding, like it's not only about generation, but how there are different aspects of dialogues, like understand emotion, sentiment in dialogues, and generate based on that sentiment and emotion, understand dialogue acts, understand intent, and so many other things. For example, persuasive dialogue understanding. Okay, and so these are the outline of my today's presentation. Is introduction, like we'll cover the introduction where I will explain the task definition, motivation, and key aspects, and then followed by models, experiments, analysis, and conclusion. So the motivation of this talk is actually from ACL 2020 keynote talk by Kathleen, Prof. Kathleen. So she said that we often design very nice, complex models and get good SOTA results, and always run for achieving more and more superior results. But we should also take a look at the problem very closely, like in which cases we fail, whether the models are just learning some surface patterns. So yeah, the analysis and debugging your model, understanding, investigating the behavior of the models is more important, okay, and often been ignored. Now, she had a famous quote that's made in SCL 2020 that bring language back to NLP that says that analyze your output, like don't just rely on the metric, but try to interpret it, try to understand how it behaves, okay, and careful preparation and analysis of the data sets. So in context of today's talk, so here is the task that I'm going to cover. So it's about tagging utterance in dialogue with different labels. And once you have these labels, how can we generate from that? So as you can see in this example, that in the first utterance, hey, I have just landed in Cambridge, the emotion is excited. And in the corresponding utterances, you can see that the next utterance, welcome to Cambridge, hope you had a pleasant flight. How can I help you, madam? So ask clarification. This is the intent. So yeah, so that is the task. So you classify every utterance based on emotion, intent, sentiment, and other labels. So we will be talking about, how you can set up and improve the utterance level dialogue understanding baselines, and whether the new architectures that has been proposed are great or not, and how can we try to interpret these models. So this is a concept of the dialogue generation model that we proposed recently. Like it's like empirically, we are still developing the part of these models. Like we are developing how you can use intents to generate dialogue, how you can topical information, personality, and speaker internal state or emotion, like E is the emotion, to generate dialogue. So this is a conceptual model, and we are trying to create part of it. So the main idea that this slide gives you is that dialogue generation is not just sequence to sequence that you do. Okay, so in machine translation, the like sequence to sequence, the idea of sequence to sequence came from machine translation. You have a bunch of source text and you translate it to target by doing sequence to sequence learning, right? But in dialogue generation, there involves many things that are very latent and you need to model it. For example, topical information, personality of the persons, what is the emotional state, and things like that. So it's not that easy to model using sequence to sequence, although these kind of models are very popular these days, but we are moving toward more sophisticated or psychologically, intuitive modeling, that is the conditional generative modeling, where you condition on these latent variables like intent, personality, emotion, and things like that. Okay, so the key aspects of the approach that I'm going to present today, and also, there are many papers on this domain by other researchers. They focus on mostly these 4 different topics. So these are conversational context modeling, speaker specific modeling, label oriented modeling, and probing strength. So let me go over it one by one. So this is a very baseline classifier, which is without context classifier. And as you can see that these are the utterances. So in a dialogue, there are multiple utterances. The blue circles represent speaker A and the orange cycle is speaker B. As you can see, there is no link between these two utterances, right? Like U1 and U2, there is no link. So that means that this model has no contextual information. Okay, so you can just send U1 to a feature extractor and can just classify it. Okay, awesome. Then the next is that we proposed in 2017. Like now, this model might look very trivial and very simple, but yeah. So, but what this model says that you can actually connect the utterances in a dialogues. I mean, of course, it will give you a contextual information. And this model is called just LSTM, as it is a contextual with respect to the dialogue. So we call it BCLSTM, bidirectional contextual LSTM model. Now, we further improved this model, which is Dialogue RNN, published in IIII 2019. So in this model, what we try to do, basically, as you can see closely, it's a very complex picture, but I will just cover it briefly. So as you can see that we have a special GRU called GRU-P, which has a recurrent relation. So this is at time t, this block is a time t, and this block is a time t plus 1. And there's a link between this. So that means that GRU-P, which models the speaker's latent state, is a recurrent. Okay, so that have a recurrent relation. So this whole model, which comprising different multiple GRU or recurrent neural networks, is called Dialogue RNN because it's an RNN that models dialogue. Okay, so I will not go into detail about it because this talk is not really about this modeling, but I have to introduce it for the clarity. Okay. So this is an improvement of that model that we presented in 2019, which is Dialogue GCN. So in this model, what is done is that we actually construct a graph based on the utterances in a dialogue. So this is a graph, and we have several heuristics of the dialogue. Heuristics for constructing the graph. So if the speaker 1 and speaker B, if two speakers are different, then there is a different age. Utterance from the same speaker are connected with another type of age, and so on. So here is the sequence of different ages that we have. Okay, like the list of different ages that we have in this Dialogue GCN. And then we have a graph convolutional neural network where we convolute over the graph architecture, and finally we will have the node embeddings, the features that we accumulate by just pooling and followed by the classification. And so till now, these models are all based on the idea that contextual utterances are very important in the classification, okay, which is, of course, like it makes sense. But we ignored the presence of the common sense knowledge in the modeling. So that we did in 2020 in our recent paper. So the idea is that when you have a conversation like this, as you can see, that you can like look, it's a beautiful day outside, why are we going? So from these utterance, you can infer some common sense knowledge. Okay, like what is the reaction of A, what is the possibility of the reaction of B, and what can be immediate effect on B. So these are the common sense reasoning that you can do from this utterance. Okay, utterance 1. And that can help you to generate the next utterance or determine the emotion of the next utterance, because you will have these common sense information that will help you to do that. So in order to do that, we modified the Dialogue RNN framework and created a new framework called Cosmic, which means is the common sense knowledge base emotion identification in conversation. So in this framework, it's a complicated architecture again, but just to briefly say, as you can see that we still have the same GRU of the latent GRU in Dialogue RNN, but this time we are invoking common sense information to this GRU. So it's a kind of information fusion where we invoke the external knowledge into the architecture. Now you can ask that, how do we do that? How do we get the common sense information? So we used a framework called Atomic, which is a common sense generative framework. Like if you give a sentence, it will generate few common sense knowledge. So, and that common sense knowledge, we've just feed it to BERT or Roberta-based network to get the contextual embeddings that we used in our network. So it's a pretty straightforward network that we created. And of course, it improved the performance. Okay, now in this talk, I will mainly focus on the two simplistic network, which is the BCLSTM, that's just the LSTM version where you connect the utterances among each other, and the Dialogue RNN versions. And it's an end-to-end model which is very difficult to train. We realized that in our experiments. So what we did, we added a residual connections from the input to the output to make things easier to train. Okay, great. So let's see the data sets that we worked on. So the data sets that we utilized in our case are IEMOCAP. So in IEMOCAP, it's a multimodal data set. So two persons are talking to each other. It's a social conversation. And each of the utterance is tagged with an emotion. Okay, so the goal is to classify the emotion. And in daily dialogue, it also has the emotion tag. In addition to that, it also has the dialogue act tags, like this is a question, that is informed, directive, commission. And this is a data set for intent detection. It's a multi-OS data set. And you can see that in this sentence, the intent is find train. In the next sentence by the user, the intent is book train, book restaurant, and so on. So your goal is to identify these intents from the dialogues. And this is a recent data set published in SEL 2019. This data set is Persuasion for Good data set for persuasive dialogue understanding. So here, for every utterance, you have a persuasive level. Like so, this for there are two persons. One is the persuader, one is the persuadee. So for each persuader and persuadee, there are these dialogue act levels. Okay. So these are the different tasks, 4 or 5 tasks that we are exploring today. So this is the brief overview of the data sets, like IEMOCAP and how many dialogues. These are the dialogue numbers. As you can see, the daily dialogue is the largest data set, which has so many dialogues, like 11,000, more than 11,000 dialogues. Yeah. So, and these are the number of class labels, and these are the different tasks. So IEMOCAP, we are classifying emotion. Daily dialogue, we are classifying emotion and act. Multi-use, we are classifying intent. Persuasion for good, we are classifying dialogue act. It's a different kind of label for persuader and persuadee. Okay, so these are the results. And as you can see that Globe CNN, it's a very baseline which does not utilize any context. And when you utilize the contextual information, as you can see that the performance jumped by 7% or even more. Okay, the same trend you can see observed for the Persuasion for Good dataset as well. Like you can see for the performance improved with respect to the non-contextual models. And when you feed the Roberta contextual embeddings, the trend is similar, but of course, Roberta is much better in the case of Persuasion for Good and these datasets, Daily Dialogue and IEMOCAP. Okay, so yeah, so we already covered the observation, so I will now move on to the most interesting part of the slides. These are the analysis, like how can you interpret the results and what are the different things that you can learn from these contextual models. So first that we did is, speaker, we actually shuffled the context. So this is a context control mechanism. So in the previous paper, like in 2018 or 2018, there is a paper published by Bengio in SEL. They claimed that if you have a contextual model for dialogue generation and if you shuffle the context, the performance does not drop much, which is a very surprising result, right? Like ideally, you can think that, in a sequential model, like utterances in a dialogue are present in a sequence. So if you alter the sequence, the performance should drop, but they observed that it does not drop. But in our case, when we shuffled the context, what we actually observed is that the performance dropped by a large margin, as you can see. Like you see this this red block, the performance actually dropped. For the IEMOCAP, it's the 2% performance drop when you shuffle in training and validation dataset. In Dialogue Act, it is 3%. Okay, and in the for emotion and for act. So what's the difference? Like why Bengio's group found that the context shuffling does not give a negative result But in our case, we found contrasting results. The thing is that they did not, like, dialogue generation, the evaluation, the proper evaluation in dialogue generation is still unclear, right? Like blue and perplexity, these measures are there, but they are not perfect. I mean, there are many studies which suggest that these are not perfect measure for dialogue generation. So in their study, they lacked that aspect, like they did not do any manual or qualitative analysis. So I guess if they would do that, they would find some negative results after shuffling the context. And another thing is dialogue generation is a different approach, or like different task altogether, where you have, for in the decoder level, you have some context attention on the encoder, right? So there you pick up the utterances that you are mostly interested to generate the next utterance. So that might be reason, we don't know, and in their paper it has not been discussed, which indicates in the future studies, in the context of generation, this should be discussed, right? Okay, so the similar trend is observed for the other two datasets as well. Now, what we also did following the ExcelNet. So in ExcelNet, you shuffle the order of the inputs and you predict the right order. So here the OP means actually order predictions. So we try to invoke this as a multitask learning platform. Like in a network, if we shuffle the context, there is a multitask loss that tries to predict the correct order of the shuffled input. So if your input is U5, U3, U1, U2, U4, you want to try to predict U1, U2, U3, U4, U5. So this is the multitask objective, and we wanted to see that whether that can improve the result, but no, it does not improve the results. It's a negative result. Okay, yeah. So next is so we already presented these observations that with shuffled context with order prediction, it just does not work. It's a this is a negative result. Okay, now controlled context drop. So this is another setting where we drop the 5 previous utterances, drop all previous utterances, or keep only 5 previous utterances, and we do the same for the future utterances when all the utterances in the dialogues are available. So suppose we want to classify dialogue at time t, so we drop all previous utterances or do just 5 previous utterances and so on. So this is the scheme. So as you can see in this diagram, so suppose we want to classify U7, and in classifying U7, we delete the past 3 utterances, which is this configuration minus 3 past, and plus 3 past is we just keep the immediate past 3 utterances, and so on. For future, we do the same. So in these controlled context drop, what we observe that long distance contextual information is very important in IEMOCAP. So the performance in IEMOCAP does not drop much when you remove the immediate the utterances from the context, but actually the long distance contextual information are very useful. And why these observations are important? Because there are many researchers now working on these kind of problems, like emotion recognition in conversations. In last 2 years since its inception, there are more than 70 papers published on this topic. So this is a popular topic, and now for a new researcher to do well, to to model context well, they should know that how context, the role of context vary from one task to another and from one data set to another, right? So yeah, these are the observations. So past utterances are relatively more important than future utterances, which is obvious, right? This is like a probabilistic modeling. Like you have past information and you want to try to interpret the future, try to understand what is happening in the future. And so one more is that training on only past utterance and evaluation on only future utterances results in poor performance. So why this is happening? So it means that, so suppose you discard all the future utterances. only keep the past utterances, and you train your model. Now you evaluate when you have the context from the future, but not from the past. So in such scenarios, the model finds very incompatible scenarios, okay? And the performance drops. So then we further probe the model with some speaker specific context control mechanism. So the two mechanisms are without inter, where we drop utterances of speaker B from the context of speaker A and vice versa. And without inter is only keeping utterances of speaker B in the context of speaker A and vice versa. So what does it mean? So suppose I want to classify the emotion of person A, and I say that I will only rely on the contextual utterances of the same speaker, that is from person A, and will discard all from person B. So that is without without inter. And similarly, I want to just keep the utterances from the other speaker and remove the utterances from the same speaker, that is without intra. So let's see, the results are very interesting. So this is the original setup. And after the speaker specific control, we have this. So with this is without intra, like this is U7, the blue circle, and in without inter, we are deleting all the utterances from the other speaker represented by the orange circles. And similarly in without intra, we are like blue one we want to classify, and we are removing the utterances from the other blue circles, like the same speaker. And this is the result. So let's talk about the result. So as you can see, that in daily dialogue and in IEMOCAP for emotion classification, look at carefully. When you delete utterances from the other speaker, the performance actually improves. So this is the globe BCLS team. This row that look at my cursor, please. This is the original results, where the in IEMOCAP 61.75 and in daily dialogue 39.27, or the micro is 53.85. And you see, after deleting the utterances from the other speaker, the performance improved. So when you remove some utterances from the context, the performance improves. That's super strange, right? But on the same data set, like daily dialogue has two different levels, right? Emotion and act. So when classifying the act, we found contrasting result compared to emotion. So here 39.9, here the performance improved for the emotion, but for the dialogue act classification on the same data set, the performance drops by 5%. So for act classification, the utterance from the other speaker are more important compared to the emotion classification. Okay, so this is the learnable outcome of this experiment. And this is of course very important, right? When you design your future framework and want to do dialogue act classification or the emotion classification, you need this kind of analysis so that you can design your framework in such a manner. And for the without intra, for emotion classification, we found that the performance dropped in contrast to without inter. So that means that the utterances from the same speaker is more important. And in the dialogue act classification, the performance does not do too much, but it still indicates that the performance actually drops. So for dialogue act classification, both same speakers contextual utterance and other speakers contextual utterance is important, but other speakers contextual utterances are more important. Okay, great. So so we even like you can observe some trends in persuasion for good data set for both persuader and persuadee. When you remove utterances from the other speaker, the performance drops, because this is also dialogue. This is also a kind of act classification, and it does not. It still drops when you remove utterances from the same speaker as well. So whatever trend you observed from dialogue act classification in daily dialogue still is valid for the persuasive dialogue understanding as well. Okay, so yeah, so I already explained most of the observations in these slides, but so a few extra points that I want to mention is that BC-LSTM model, like the basic LSTM model, is incapable of choosing the right context for prediction. So, so in a scenario, like you should, like if you design a model, if you design a model, your model should be good enough to pick up the right context for the classification, but these models cannot do that. So that's a future work that we should try to do, right? And a unified model may not be good enough to address all the tasks that we are seeing in these cases, right? So we designed a unified model, but for sure it's not good enough, because in some cases the performance drop, in some cases the performance improves. So we may need task specific modeling. Okay, so that's one of the major learnable outcome of this experiment. Okay, so then we studied this, like a role of context further, and did some style transfer to the context. So what is style transfer? So style transfer is transferring a piece of text from one domain to another while preserving the underlying content. So as you can see in this example, horrible food and terrible service. And if you can transfer the style, you can keep the domain same, that is food and service, but change the sentiment over the amazing food and perfect service. So you are transferring the style from negative to positive. Okay, and you are doing it for the context, and let's see what will be the outcome. Sorry. Yeah, so this is the protocol experimental design. For each target utterance, we change the style of the contextual utterances. If the contextual utterance is in positive emotion group, so suppose, like I want to classify an utterance which is angry, but in the context there is frustrated, so that is a negative emotion. We change the style of that utterance into positive, and vice versa. And for the neutral utterances in the context, we are not doing anything. Okay, so this is a visual explanation of what we are doing. So this is a neutral utterance, and we want to classify this utterance in orange color. So you cannot be serious. So this utterance we want to classify. The original ground truth is angry, and the original prediction was angry. Now we are changing the style of the future, style of an utterance in the future. So the original utterance was, hey, I've always gone hunting or fishing on vacation. I'm sorry that bothers you. So we are changing it. We are changing the style of this context to, I have always gone here on vacation and had great fishing experience. So we changed the style. And if you ask me, how did we change the style? Well, we designed a style transfer classifier for it, style transfer generator, sequence to sequence generator, which changes the style from the source to target. And there are publicly available data sets for doing that. Like style transfer is a very interesting domain. You can read about it, and there are parallel corpus for that. So we trained it, and yeah, and we obtained these automatically, or automatically obtained such sentences from the generator. So by changing it, as we can see that the prediction changes. So the original prediction was angry, the ground truth was angry, but after doing the style transfer of the context, the prediction is neutral. Okay, great. So let's see the result. So this is the original result. Okay, before the style transfer. Then after we did the style transfer, you see the performance started dropping. So this is the style transfer of past and window of 5. So in past 5 utterances, we are changing the style. The performance dropped, right? From 61.9 to 58.28, from 41.16 to 36.13. And the same tradition, when you change the style of the future, the performance does not drop as much as we observed in the case of past, but it still drops. Okay, and when you change both past and future style, the style of the context, the drop is even more. Okay, so past and future context are very important when you are doing the analysis, and if you just keep the content same but change the emotion, that will also affect the performance of the models. Okay, so and we found that the long distance utterances, which we also proved in our other experiments, in this experiment we also observed that long distance utterances are really very important in the case of IEMOCAP, because you see that the drop is actually huge when you change the previous 10 utterances. The drop is huge. Like previous 3 utterances, if you just change previous 3 utterances, the drop is 2.5%. But if you change the style of previous 10 utterances, the drop is more than 5%, like approximately 6% drop we are observing, 6.5%. So the long distance utterances are very important in the case of IEMOCAP dataset. Okay, so we did more probing to understand how context behaves. So the next is the paraphrasing and the spelling based adversarial attack to the models. So paraphrasing, I mean, we all know paraphrasing, right? That the semantics will be same. We will just paraphrase the sentence, and in spelling, we will just corrupt some of the words in the context, but the remaining words will be the remaining words will be same. So let's see, like in paraphrasing, like if a model is very good in paraphrasing, it should not drop the performance much, right? So let's see, visually, let's see that what is happening. So we want to classify this orange text, like this block. I have already told my buddy. So this block we are going to classify. The original ground truth was neutral. The original prediction was neutral. And we are changing, we are paraphrasing the context. So this was the original, the the crossed text. John, I was looking through some magazines for ideas about where we might go on vacation this year. And the paraphrasing is just, John, I'm searching for some ideas about where I could go on vacation this year. So the meaning is same, just we paraphrased it. And even in the future, we are doing the same. You cannot be serious, you better be serious. Okay, so we just paraphrased. So the context is same, the semantic is same, but as you can see, the performance changed. Like the prediction changed from neutral to angry if you just paraphrase. So that means these models are not really solid, and they really like they may really learning some surface patterns, and they are not good enough when you attack using paraphrasing. So yeah, so similarly for the spelling corruption, so we are just changing the spellings of some text, and as you can see that it can alter the meaning to some extent. Like if there is an word which is very important, if you are changing the spelling, it will affect in the meaning, right? And that reflects in the in the result, so which is not surprising, of course. And so this is the original result before any paraphrasing or any adversarial attack, the like spelling based attack. And after the paraphrasing attack, in the window of 10, 3, 5, and 10, from in both past and future, you can see that the performance is actually dropping huge. Like similarly, like when you apply the paraphrasing on both past, future, and the target utterance, the performance dropped. On persuasion is 12%, on the emotion it is 10%, and so on. Even for the spelling based attack, we observe the same trend. But this is not surprising for the spelling based attack. But although we expect our models to automatically detect the spelling errors and correct and fix it, right? I mean, there should be capability, because if suppose you have a chatbot and you in your chatbot you want the emotion detection capability, and you have some spelling mistakes, which is very frequent when we chat with someone, then these models would not work well, right? And this is a bit surprising result, and it shows that we need to improve our models a lot. Okay, and now this is very interesting when you compare your modeling with when you compare your modeling with the non-contextual, like contextual versus non-contextual, like this is globe CNN is a non-contextual model, right? And if you do paraphrasing attack, adversarial attack on globe CNN and compared to be a LSTM based model, you see that the performance drop in the globe CNN model is larger. Okay, see, this is the performance drop in globe CNN, like 23.27% compared to 6.17% in when we use the LSTM based model. So what does it suggest? It suggests that contextual models are difficult to fool compared to their non-contextual counterparts, right? So that's the thing. And I mean, and this is very interesting, because the contextual models like BART based architecture or ExcelNet based architecture, what you do there, you mask some words and try to predict it, right? So that gives you the ability to have more contextual understanding, uh, and of course you can guess the context, and that is why it is harder to fool. Okay, and attacking past utterances drop the result more compared to the future utterances, which we also found before, that past utterances are always more useful. Okay, now this is one of the this is also another interesting experiments that we did. This is the performance for level shift. Now, as you can see that in this slide, I'm showing that for a same speaker in IEMOCAP dataset, you can see a similar trend that angry is followed by angry, excited is followed by excited, frustrated is followed by frustrated, and so on. For in daily dialogue, there is no such pattern, but for act, there are some patterns, like question is followed by inform, and so on. And for the other data set, there are such kind of, like, not that frequent, but there are still some patterns in multi-OS data set, right? That like like find police is followed by find police, book train is followed by book train, and yeah, so on, like some level level continuation. And we wanted to see that when a label shifts, when a label shifts, how does it affect the performance for both cross speaker and the same speaker? Okay, so let's see the results. So first, the protocol of the experiments. So in intra-speaker shift, the level of the utterance is different from the level of the previous utterance from the same speakers. Like in such scenarios, whether the performance drops or the performance remains same. And inter-speaker shift, when the level of the utterance is different from the level of the previous utterance from the other speaker. Okay, so as you can observe in these blocks, there is a strong level correlations in the data set. So when we analyze the data set, like when I start the presentation with Prof. Kathleen's ACL keynote, 2020 keynote, I mentioned that we should understand our data, right? So in our data set, there are such long level dependencies, especially in IEMOCAP and Daily Dialogue Act. And now we will see that how does it perform when there is a speaker shift. So what do we mean by the speaker shift? So visually, as you can see, that the inter-speaker level shift, this is speaker A, the green, and this is speaker B. So the act was question, and in speaker B, the act changes to inform. So this is inter-speaker shift. And the dotted line, these are the dotted lines. So the greens are the same speaker. So in the previous utterance, the act was question. In the second utterance, the label shifted to directive. Okay, and similarly in this picture, you can see that the intra-speaker level shift is frustrated to anger for the same speaker. Okay, and from the cross speaker, it is frustrated to neutral, frustrated to neutral, neutral to frustrated, and so on. So let's see the result for the intra-speaker shift. As you can see that as you can see that the performance dropped by huge margin on IEMOCAP dataset and Daily Dialogue Act dataset, which is what we expected, right, from the dataset, because in dataset it is biased because there is a very large level dependency among the consecutive utterances of the same speaker. So when there is a shift, it fails to detect. Okay, so and the drop is actually huge. The drop is by huge margin. And similarly, for the inter-speaker, we observe the same trend, but for daily dialogue, we do not observe any such trend, and also for the other data sets, such trends are not there. Okay, great. Now, when we converted the emotion to sentiment, like anger, frustrated, or sad, or negative sentiment, and joy, happy, these are the positive sentiment. Did you observe any improvement? Actually, no. I mean, it's still the same. The performance still dropped. Okay, like sometimes what happens, like, that you predict an angry utterance with frustrated, right? But when you convert it to the sentiment scale, the prediction should be correct, right? Because emotion is more fine grained. But we observed that the performance was still worse. So that means that simply on IEMOCAP and daily dialogue, these contextual models are not performing well. I mean, for the emotion shift, when there are emotion shifts. So this is a new task which is newly introduced, and there are some submitted papers that I handled in this year's AAAI, which try to address this task, because it's very difficult to to capture the shift correctly. It's very difficult. So this is a new task for the future work. Okay, so some case studies about the work. So I'm toward the end of the presentation, so maybe 10 more minutes. So you can see in this example, so this is a contextual co-reference, right? So suppose, so in this utterance, you observe that, hi, I would like to find a restaurant located in the center, please. Then in the next utterance, and the intent is find restaurant in the in utterance one, but in the next utterance you say that modern European please, and I would like some place moderately priced, which is also the intent is find restaurant. But how does the classifier resolves it? Because you do not mention explicitly that you are finding restaurant, so it takes help from the context and say it tells you that this is about find restaurant, like some place is linked to restaurant. Okay, so there is some complex co-reference in the dialogue level. Similarly, other contextual dependencies, you can find that I need to find a guest house with a 3-star rating, which is the contextual dependency. You can find that, no, I don't. I want one that includes free Wi-Fi. So you are implicitly telling that you need a hotel that has free Wi-Fi, but there is no explicit mention. So without context, you cannot really predict it. Okay, so there is this contextual dependencies are there. There are this label dependency, as you can see that from this utterance, like frustrated to anger, there are this label dependency, also other contextual dependencies are there. Now, the thing is that the case studies that I am showing you, and in most of the papers, you would not find this. Okay, like you will see a lot of visualizations, even in many of my papers. Like I must acknowledge that there are nice visualizations and a nice thing, but are these case studies, universally accepted or appropriate? In this case, these are cherry picked, and in many of the papers that you will find, the case studies are cherry picked. Okay, so there is no guarantee that these models are able to find such context saliency automatically. Surely there is no such guarantee, right? Like our models cannot tell it. And we can cherry pick key contextual utterances and drop them to explain performance of the baselines, but that is not an optimal way. Like if you have a large, huge data set, you cannot do that. So the model should be capable of explaining their answers. That should be our goal. So towards the explainable AI, like we should have models that can explain the results. Some of you can tell that there are attention mechanisms that can do that, but the contrasting results and studies are also there which suggest that attentions are not enough. Like they are not really suggestive interpretability of your models. Okay, so these are the future directions. The contextual models should explain the factors they rely on for decision making, and contextual models should select the right context for predictions. BCLSTR model is not effective for context modeling in persuasion for good dataset because we saw that the performance is worse than non-contextual models. The perturbation strategies present in this work can be adapted to other contextual tasks such as dialogue generation, which we are now doing. The multi-party dialogue understanding we are not covering in this case because it involves very complex co-reference. And speaker-specific model like dialogue are an output from BCLSTM in most of the data sets. So it would be interesting to explore the speaker-specific aspects of the models, like probing the models from the speaker-specific point of view, like speaker state and things like that. Okay, so in conclusion, like how we can use the studies in generation. So this is the new work that we did in IEMOCAP 2020. We called it MIME, that is empathetic, like you mimic emotion to generate empathetic responses. So what we are doing, just to say briefly, so this is an input and this is the output. As you can see that these are empathetic. So what we are doing here, this is a transformer-based sequence-to-sequence model, but inside the model, we have emotion recognition techniques in conversation. Then we have some variational sampling techniques that groups the emotion into positive and negative category, and it will mixture the emotion from both the categories. So we have a category for positive emotions, we have a category for the negative emotions. Then based on the input, we will do variational sampling, variational technique to sample from these two groups and fuse that with the encoder output for the generation. Okay, so here we are fusing and here we are sampling. Like one emotion is the mimic group. Like if your input emotion is anger, would you like to support the anger emotion and generate an emotion which is negative, like related to anger? Or non-mimic group, like you are replying with an utterance that is happy. So I am uttering with anger, but you are empathetic to me and you are trying to console me. You are trying to give me some positive vibe. So this is the fundamental of mimic and non-mimic group, and we are fusing it. So we are creating the mixture of emotions here, okay? And send it to the decoder for the response generation. So this is that we did based on the emotion recognition in conversations and the techniques that we have explained, like the motivation came from those techniques that we have explained. And these are the results that you can find. The codes are public on our lab's website. If in fact, whatever we have explained, I have explained till now, the codes are available on the GitHub, on our lab's GitHub. So as you can see, this is the user's utterance and this is the empathetic response till now. Then the user says another utterance, utters another utterance, and our empathetic response is this. That must have been a very beautiful memory, where the gold response was, it sounds like a great experience. And the existing work actually did not do quite well. And this is a general trend throughout the data set. Okay. So as you can see that this is empathetic, right? Okay. So now this is a new work that we have been doing since past few months. So we are introducing a new data sets today in ICON, which is Recon, a data set for recognizing emotion cause in conversations. And this data set is publicly available. We are releasing it today. So this data set is about, like we have said about that how contextual model behaves, but we also mentioned that how much context is needed and when to rely on the context and how we rely on the context. There is no baseline or there is nothing to evaluate it. So this is the data set that can do it. Okay, so in an contextual model, like emotion recognition model, you should be able to, like the contextual model should be able to say that what is the cause of the emotion, right? So this is the data set for that. As you can see, like I will go over some basic properties of this data set that we have created. So suppose in this 4B, like utterance number 4, speaker is B and the emotion is happy. So we have not decided yet. There are a lot of things to sort out. So how can you classify this is happy? What is the cause of this happiness? So the cause of this happiness is in the context. The context is you are engaged. What a beautiful engagement ring. We fell in love at first sight. So these are the utterances that are cause of these, apparently mutual utterance in utterance number 4. And this is very latent, and you need a lot of reasoning capability to annotate this dialogue with the corresponding emotion and find the emotion cause, right? So these are the different things that we have in our data set. So for example, in this case, you can see that all the previous utterances are neutral, and suddenly this is the price is final. It says that it sadness. But what is the reason for the sadness? You can see that these are the contextual utterances that are the reason for the sadness. So the person, the buyer, is not ready to buy it for 2,500. The buyer wants to stick to $2,000, but so that makes the seller unhappy because the seller is unable to buy, it's unable to sell it, right? So that is the cause. So it needs numerical reasoning and of course affective reasoning. And sometimes it does not depend on the context, which is a very easy case. Like in this case, you can see, yes, I think so. It's not very expensive. It's in the right area and it has everything that we are looking for. So you can clearly see that it's not very expensive. It is in the right area. And so this statement, this incident, this event, this event makes the person happy. So that is the stimuli of the emotional response. So this is the statistics of the data that we created. We have 1,106 dialogues. We have 11,000 utterances. We have annotated more than 5,861 utterances, but one utterance has multiple causes. As you can see that the number of causes per utterance on average is 1.69. In the daily dialogue in IEMOCAP, it is 2.34. And when we combine it, we have approximately 9,915 utterance and cause pairs. So it's a decent data set to train your deep learning models. And we also created some negative samples that makes the data set larger, even larger. So this is the final data set composition that we are going to release. And as you can see, that there are two subtasks. This is the causal span extraction subtask, like given a conversation and an utterance UT, extract the span from the conversational history that is relevant to the emotion cause of the utterance UT. So in this setting, we use span bird and Roberta base, and the performance is actually very poor, as you can see that it's not much. So it's a difficult task. And the second task is the emotion entailment. Like if I give you an utterance, contextual history, and a target and another utterance in the context, you have to predict whether UC contains the causal span of UT, whether the UC is just an utterance in the conversational history. In this setting, as you can see, we must look at the positive F1 because this is the most interesting thing. For the negative samples, it's very easy. So the performance is very low. Okay, so a very, very difficult task to crack. So this is the link to access the paper and the data set. I hope you will find it very useful. We are modifying the data sets and we'll keep updating it. And yeah, so this is, to conclude my presentation, this is our lab declare. You can, and you are of course welcome to join our lab, like if you are willing to. This is the lab members. We are not a big group yet, and yeah, they are doing all the great work which I presented today, so shout out to them. And yeah, thank you so much for inviting me, and it's my pleasure. Thank you so much.
Thank you, Soujanya, for the wonderful talk. We'll take a few questions and
Yeah.
we have a few questions. So there is one very generic question. Probably we'll take it at the end. So one
Hmm.
question is from Professor Radhika Mamidi. So Professor
Hmm.
Mamidi, would you like to ask yourself? Professor Mamidi?
I think I can.
Okay.
I can.
Okay.
I understood the question. So I think the context question is about the anaphora resolution, like context of anaphora resolution and things like that. Actually, you were right. So like when you drop the context, the co-reference, the anaphora, these kind of things, we are deducting that from the data set, which are affecting the performance. So yeah, I mean it's an it's not a surprising result like we expected it. So and the main purpose of that work was to evaluate how much context is important. Like in IEMOCAP, we found that the long distance co-reference, you can say, are there, the like long distant contextual dependency is there. In other data set, the long distance contextual dependency is not there. The future utterances are also providing contextual information. So these are the things that we learned from the experiment. But of course, like the performance dropped is because of the like lack of co-reference reliance. Yeah.
Thank you. I'm Radhika.
Hi.
Thank you, Dr. Shadakta, for taking it. I did not have the speech option earlier, so I could just chat. So the very idea was a bit, revolting, shifting around the utterances, So that is why I felt you would see the whole conversation will not be meaningful if you, move around the utterances. That was the whole
Right.
point.
Yes, definitely. Like if you drop the if you drop the utterances, the conversation will lose some semantic, but will not lose the full semantic because you will still have the target. And sometimes the target contains the enough evidence for the right prediction. For example, your target is just an emotional expressions. It's great, so nice to be here. Suppose this sentence does not need any contextual information to predict the emotion on the or the sentiment, right? So in
No,
this kind of case,
for example, if I'm telling it in a sarcastic way, I would like to know, it will still be related to the previous input.
definitely, yes. Context is very important, and this is why when you drop the context, the performance also drops, right?
Drops. Yeah.
Yes, of course. I mean, it is very important, but not always.
Okay. Thank you.
Thank
Thank you.
you, sir. So another question is from Professor Rajesh Sangha.
Yeah. Mhm. In slide 44. Yes. Should I read it out? Or
Y- Yes.
Yes, Professor
I mean,
Rajesh.
Professor Rajiv, you can also read it out. I mean, no problem. Yeah, if you are not
Uh,
on mute. Yeah.
yeah, I'm no longer unmute. On slide 44, when you had done a paraphrasing,
Mhm.
if you can go to there, it's very clear. So it's a paraphrasing in the first part of the dialogue. So
Yeah.
there are two I's there. I am searching for some ideas and where I could go on vacation. So the second I
Mhm.
changes the meaning slightly. Earlier it says where we can go, here it says where I could go. Do you think it would make any difference? Models are sophisticated enough
Uh,
to catch that.
yes, in this context, okay. So sometimes, like, yeah, in this case, it is changing the meaning a bit, but not to that extent to alter the performance of the prediction. Okay, but the models are not really that sophisticated. This is why the performance dropped, right? The original prediction was neutral, but when you paraphrase the performance, actually the prediction was wrong. Okay,
Yeah, yeah.
so and there is no explanation why the prediction is wrong. I mean, this is the problem of the models. Like we create the models, but when we just paraphrase and this paraphrasing is not that wrong, like which can alter the prediction.
So one question which is about anaphora. In dialogue, there is a lot of anaphora.
Right.
And do you do any processing with anaphora before you hand it over to your system?
No, not
To the
yet, not yet,
neural
not
network.
yet. Yeah, but we don't do it yet. Also because that the anaphora resolutions, like the systems are not that well, right? It's still very challenging problem, and a bad anaphora resolution can further adversely affect the performance of the models, right? So we have not yet done it. Yeah, but it's a good point. It's a good point to explore. Yeah.
Okay, okay.
Thank you. So, another question is from Jafar Ali, and his question is, how do you account the topic and cohesion over the dialogue flow?
Yeah, that's a very good question. So it's very unfortunate that in in most of the data sets we do not have the topical information. So we either learn the topic implicitly throughout the learning process, or we just don't count on it. But there are some data sets in the context of dialogue generation released by Facebook AI Research. They are giving the topical information, like some background information about the dialogue, so that you can at least generate some coherent dialogues. So it's a very important, like in our case we are not considering it, but we are just saying that this is an important thing in the dialogue modeling, that the topic is really important. Yeah, this is a conceptual model, a concept of dialogue generation model, like, yeah. Yes.
Another question is from my family. The question is there any specific reason of using GRU in the cosmic model and LSTM in BCL STM 2017 instead of transformer in either case?
Oh, not really. So, like, I would say the like, so in 2017, I think GRU was not that popular yet. So we just used LSTM, and later we started using GRU because we have less parameters and it's fast, and the performance is similar to LSTM. Like there is no really significant performance difference between GRU when you use GRU and when you use LSTM. So it's just a choice. Like you can just replace GRU with LSTM. I guess just that's the engineering trick, and the performance should be same. Like you can try. Yeah.
Okay. One last question, and this is very generic question, so probably other panelists member can also answer to this. So there is a question from Shubham Shad Khan. I'm very new to NLP, so I want to know the proper roadmap for NLP. What are the basic needs to do a project on NLP?
Okay, that's a very good question. So I would always encourage you to do not run after the state-of-the-art performance, or do not just browse through the conference papers and try to outperform the existing works. I would suggest you to read the basic books by Jarobsky Martin, and there is a famous book and for deep learning for NLP by Goldberg. You have Goldberg. So these are the books, basic books that you should read. And yeah, I think that should give you a clear idea, like in which direction you should go. Like I would not suggest you to just trick your model, just engineer your model and publish the papers in the conferences. I mean, that's a okay thing, but that, yeah, like that is not a good thing to do, like not recommended thing to do. Yeah.
So would you like to add something to it, Professor Pushpa, Professor Raji, Professor Dixit?
No, I think yeah, excellent talk, and I think it brings back the issue of how important language is.
Yes.
And
Thanks.
pure machine learning without any understanding of language will not take us very far.
Very true. Very true. Yeah. Yeah.
Thanks, sir. We shall conclude this session. Thank you, Dr. Professor Soujanya Poria. Thank you for talk.
Thank you so much for having me. I wish you all all the best for the rest of the conference. Yeah. Thank you so much.
Thank you.
Thank you.
Next
Thank
time you should physically visit us in the conference next year. Okay.
I will love to.
Thank you.
Thank you.
Thank you.
Thank you. Bye.
Bye, Soujanya. Bye.
Bye.